Hello, I'm Blair Johnson at the University of Connecticut, and I'd like to talk a little bit about making sense of heterogeneity in meta-analysis. Eventually, I'll explain why heterogeneity appears in quotation marks. So the goals of meta-analytic statistics are to examine mean tendencies in the data that are gathered in a meta-analysis. We have to look at model fit statistics, and we might want to look at moderators, or sometimes they're called effect modifiers or subgroup analyses. We'll have tests of significance for those moderators, and we'll have model fit statistics. And we might want to think a little bit about outliers, although I think in this talk I'll do less with that. I'll mention it in passing a few times. So let's see how we can manage the subject of testing models in meta-analysis. And yeah, you see the point there. So what are the necessary statistical ingredients? You want effect sizes, and here, see, I'm defining effect size as a t, a common way of thinking about it. So you define them in one form, not mixing with others, the standardized mean difference, a log to odds ratio, Fisher's z-transform of R, or arithmetic means, etc. You can do a lot of different things with effect sizes. Put them in one form. And then you're going to have a variance calculated for each effect size. And Lipsy and Wilson provide a really tidy table of these equations. Those define the weights for analyses. So you have it. Here is a representation of that table. A lot of equations, but essentially in the second column, first column you've got effect size type. In the second column, the statistic defined in a simple way. And then you've got two columns that are essentially related to the weights, the standard error and the inverse variance. And in meta-analysis, we use the inverse variance routinely, although some equations out there will use the standard error, so it's good to have your hands on both of those. I'll show you a couple of examples. In the case of Pearson's product moment R, there's your effect size is the R, and you can transform it to the Fisher's form of it using that equation. And that's the effect size stat. And then the standard error and the inverse variance look like this. It's very simple. You can see how standard errors get smaller as you get bigger and bigger n's. So what we're doing is valuing the studies. Well, I'll show you that in a second, but we're going to value the studies more that have greater n's. In other words, they're more precise. And the inverse variance for the R, the Fisher transform is, as you can see, there's just n-3. So that's one example of the conventional statistics that are used for one effect size. Here's the standardized mean difference. It's a little more complicated. The effect size at the top there is very standard. And then here you've got the ES prime, implying that you've got a correction that you're using and multiplying it by. You've got a correction for the effect size that this is the sample size bias introduced by Hedges. And so that's the corrected form. And then the standard error for that is defined this way. Very complicated, long equation. You've got the different sample sizes in there that you're comparing between the two groups. And then here's that effect size itself shows up in the standard error. That's just how the math works out. And the inverse variance, equally complex, but essentially what's going to happen once you get to doing meta-analytic models is that the studies with bigger samples are the ones that are going to have more weight in the analysis. I'll literally show you how that's the case. So in meta-analytic statistics, the overall trends, a simple fixed effects model for every effect size t would look something like this. In theory, you've got an observed t that's equal to the population effect, the theta, plus some amount of error. And those things conveniently cancel out once you go to the next phase, and so we tend to ignore them at that point. So that model assumes that variation in the effect sizes is only due to sampling error. That is, they're all approximately equal to the population value. Of course, you're going to have variation from one to the next, but it should all be inside sampling error. All right, clear enough. Once you get to the meta-analytic statistics, here's the simplest meta-analytic model. You're taking the weights, multiplying each one by its effect size, and summing them, and then dividing by the sum of those weights. Very simple. It's a weighted average. Here's the calculation for the confidence interval for a mean effect size, and you see the calculation here. Again, we're using the sum of the weights. The inverse of that ends up plugging straight into your CI calculations, and you've got an upper and a lower bound on the confidence interval. And then the fit of the mean effect size model is defined by the homogeneity of the effect sizes that underlie it. So Q is defined this way. Again, you've got your weights here, sample size weights, the kind of thing I just defined, and you're taking each individual effect and subtracting from it the grand mean, the one you've calculated up here. That's a weighted mean effect size. You're squaring those deviations, otherwise they would sum to 0. And that comes out as approximate chi-square distribution with k minus 1 studies, where k is the number of studies. Always use that for number of studies, not n. Okay, well, there's a recent development. We have a new way to represent homogeneity of research findings. So a little history for you. Cochranes Q, defined way back in 1954 in a very odd way and not easy to find if you go look at it. But it defines variability in findings surrounding the weighted mean effect size. And it's the same thing as Hedges H or Hedges Q. Q evaluates the hypothesis of homogeneity, although conveniently it's become known as a test of heterogeneity. Squared differences between observed effect sizes and the overall mean effect size make it clear Q is testing the assumption of homogeneity. So let me get up to, there's our equation again, and you can see small values imply homogeneity. So deviations from that mean deviations from homogeneity. Thus, we're testing the assumption of homogeneity, not the assumption of heterogeneity. So, in fact, I note here, the chi-square value has infinity for an upper bound, so I don't think you can actually define heterogeneity in an ultimate sense. Anyway, if you have a significant Q value, that implies an inference of heterogeneity. And so conventionally, we will say heterogeneous, meaning that there's more variation in the effect sizes than sampling error alone would expect. Okay. Q's value, Q's value depends on the number of studies that you're integrating. So that makes it difficult to compare between meta-analyses and portions of meta-analyses. So it's become quite routine to use I-square for that. Higgins and Thompson used the Burge ratio and a lot of mathematical operations to move Q in the range of 0 to 1 or 0 to 100 if you use the percentage form. And that makes homogeneity values comparable even when K varies. Okay? You see how to deal with some subtleties here. So the equation looks like this, and you would multiply it by 100 to get a percentage. And if you have a negative value, you change it to 0. Those are the rules right now conventionally. Here's an example with a very low I-squared value. This was not significant. It's essentially showing you a normal distribution, not much happening. And that's looking at HIV prevention for adolescents. 0 defines no difference between treatment and control in terms of how much abstinence the adolescents exhibited after being in the intervention compared to controls. So the interventions were not moving them very much. In fact, there was a slight positive tendency in that meta-analysis that came out of our group back in 2003. So that's homogeneous. We only see sampling error there. I-squared was not significant. And there I show you where the mean was. In fact, the mean just barely made significance. In this next example, the same meta-analysis looking at the adolescents' use of condoms or avoiding unprotected intercourse. And there you see a more moderate amount of I-squared, of heterogeneity as it's often defined. There's the mean value, shows up about the same as the last graph. But you see there's a lot more spread around it, and the I-squared statistic is picking that up. So in this case, you have what Higgins and Thompson have labeled medium heterogeneity, which is perhaps an arbitrary label, but at least it's a little bit descriptive. I-squared was statistically significant. At least you can infer heterogeneity in this sample of effects. Here's a more extreme example. A dissertation conducted by Tobler back in the 90s on drug abuse prevention, widely varying effects of drug abuse prevention efforts. So, and here is one case where I'll mention outliers, because here you've got a boomerang effect where the controls are doing far better than the treatments. So something went horribly wrong in that particular trial. And there's some really wonderful success stories out here, but they're not mirrored on the other side. And so it raises questions of publication bias as well. But that's a subject for a different talk. We did a meta-analysis incorporating 62 meta-analyses or portions of meta-analyses that examine health promotion effects. And so that's over 1,000 studies, and mostly those are randomized controlled trials. And you can see that quite a lot of these studies had very large I-squared statistics when you compare across these. So 68% of them were significant, implying heterogeneity. It really does look routine to get heterogeneous effects. Thus, the hypothesis of homogeneity is usually rejected. And the meta-analyses for which it was not rejected had far fewer studies than meta-analyses that rejected it. So it's one of the problems with Q and R squared is that they are subject to statistical power considerations. And if you don't have a lot of studies, you may not be able to detect deviations to the hypothesis of homogeneity. So another example, here's gender differences in social dominance orientation. Yicheng Li, Felicia Prado, and I published this in Psychological Bulletin back in 2011 if you want to look it up. But we looked at gender differences in this, and you see the definition there. Conventional hedges is corrected, standardized mean difference. We called it D. And the weight is the same that I just showed you. And here I've run David Wilson's macro with some enhancements, showing what the mean effects are across this whole literature. So this output includes two versions of the mean assuming random effects. The confidence interval becomes somewhat wider because the population variance is added to the sampling variance for each study. So that's what's happening down here. The means are about the same. You're not getting a different answer in terms of detecting that there's a gender effect, but you can see that there's much less power in terms of the random effects version. The z-test kind of directly shows you that because it's half the size in the case of the random effects versions and compared to the fixed effects one. Now, if you're going to pick a version of these and you're doing this particular analysis, I would suggest the full information maximum likelihood version. So I would say the better option is random effects 2 to be reporting, although, like I said, in this case, it doesn't matter very much. This model, I should say, used an enhanced version of Wilson's mean ES macro for Stata. I basically added in, along the help of a former student here at UConn, I-squared statistics because everyone wants them, and it saved us the trouble of having to go out and calculating them for ourselves. So there they are. So here's the overall gender differences. You see again the funnel plot of effects. And this is like the other ones, a contour enhanced funnel plot, which helps you to see where significant differences are showing up. You can see how normal it is. I mean, I don't think there's any hint of publication bias in this, although again, this is a more complicated thing. But it's kind of beautiful. You get the funnel shape outlined by the effects, and it takes the very same shape as the contours here. The contours are drawn around the 0. And so you can see how the mean effect, which I've drawn with a line here, is well to the right of neutral. It seems to be quite a robust effect, a difference between the sexes. So in fact, it shows males being more dominant than females, to put a point on it, since I don't think I've said that yet. The I-squared for this one, we reported on the last slide, 64.7%, and here's the confidence interval for it. We're going to infer heterogeneity. So we want to try to explain why is it that these studies are getting widely deviant results. So look at this. Significant effects are quite likely, significant even defined relatively conservatively, the blue zone. They're happening all the time. Whereas we're not getting a lot of boomerangs. There are some that are bordering on significance over here, but there's quite a big spread between the effects. That defines heterogeneity. We want to try to explain that. So usually you have some a priori hypotheses about sources of heterogeneity and effect sizes. In fact, many meta-analyses in social sciences or even life sciences these days are not very interesting unless you want to think about these kinds of dimensions. So you can model features known to the studies, what kind of intervention features they used, what kind of samples they used, or things about the environments where they were done as potential associates with the magnitude of effect size. So these are called things like, terms like subgroup analyses, moderator analyses, effect moderators, and even meta-regressions. And I'll come back to that and again explain I've got quotation marks there. Those all use analogs to ANOVA or regression, and they add weights in then. And that would be the inverse of the variance for each study. You already saw how to define the variance. So the fixed effects weight is essentially the sampling error weight, and it assumes that there's greater precision in studies with larger samples. And then the other one would be the population variance and effect sizes, which in each analysis is a constant added to each study. Whether you use ANOVA or regression for these, both are ordinary least squares or OLS models. Okay? Emphasis on that. They're really doing the very same thing, and the examples I'm going to give you right now will show that explicitly. So here's a categorical model. You're just going to break your effect sizes into 2 or 3 or however many discrete clusters you have in your categorical variable. And so this example will use Wilson's meta-f macro in Stata, and we'll answer the question, do studies in the US get bigger gender differences in social dominance orientation? Just a simple thing. So here's the output from that command. It incorporates random effects. It's a good way to put it. You're incorporating random effects. It's not necessarily a random effects model completely. It actually has fixed effect slopes and random effects constants, so it's mixed. But if you said that your models incorporate random effects assumptions, probably the reviewers will let you go by, and you don't have to contest that. The QB statistic provides a test between the means for each category in the model. So if you had 3 categories here, it would be like an omnibus test for differences among those means. In this case, we only have 2 means, so there's only 1 degree of freedom in the contrast, and there's only 2 means that produce here, so that's relatively simple. The QW provides a test of model specification. You can probably ignore it when you're incorporating random effects variance components, but it is very useful when you're assuming purely fixed effects models. In fact, I have concerns about the calculation in the Wilson macro, and I'm not absolutely positive that it's correct, at least in the instantiation here for Stata. If you look at the weighted mean effect sizes for each category, then you see the pattern of that significant difference. The pattern is that studies in the US get a larger gender difference than studies elsewhere. Okay. Now, if you look at the confidence bands for both of those mean effects, you can see that although there is that gender difference being bigger in the US, both of those mean effect sizes are significant. There's no 0 in that confidence interval, therefore they are significant. The within category QW statistics reveal that the mean effect size is a good fit for the studies within each category. Again, I have reasons to doubt this calculation because when I do the mean ES within these 2 levels, I don't get exactly the same answer. So I think there's some problem with this macro. But this is how you would interpret the output, even if you can't trust it. I apologize about that. We need to troubleshoot this thing. And then down at the bottom here, you've got the random effects variance component. So that is tau squared that you see at the bottom. And you'll see in the next analysis, we estimate it very similarly when we use the metareg command. So categorical models can also be examined, meta-regressions. In fact, I very rarely anymore use meta-f except when I'm doing bivariate model testing. Usually I've got big databases where I can look at a lot of covariates all at once, and so I'll mix categorical and continuous variables in meta-regressions all together. It's the only way to do it. So one caveat about running categorical models is they are, well, pretty much always bivariate and only bivariate. So an advantage with going to meta-regression is that you're going to have a lot more flexibility about what variables to include. So why the quotation marks? Meta-regression has them. At least from one perspective, you can argue it's badly named. Meta-regression literally means regression of regressions, but it rarely has that application. Just like meta-science is science of science, and meta-analysis is analysis of analyses. So meta-regression is kind of silly because it rarely is the case that you are regressing regressions. I'm not even sure I've actually seen that done. I think in theory it could be done, but it's extremely rare. So I think what you should think about is that meta-regression is actually a truncation of the term meta-analysis regression. It's just easier to say meta-regression than it is meta-analysis regression. So these take the formal form like this. You're predicting what value a predicted effect is. That's why I always say t hat. So this is a predicted effect size from these different carriers. So I define all these. So here's your generic effect size for study I. And now you've got to fill in the equation on what its values are for the other beta weights and the values that they take. So, and the beta weights themselves, the regression coefficients, these are unstandardized. They're the unknown regression coefficients, and you learn them when you fit the model. So I'm going to show you examples of this, and this will all hopefully become crystal clear. So, oh, and if you want a good source, I mean, the original and still venerable and unchallenged champion, I think, in terms of describing the mathematical assumptions of this kind of model, go and look at Hedges and Olkin's classic book. So here we've got an example in the same, with the very same model in the very same literature that I just showed you. And I have just, again, examined, oops, this is bad. Here we go, good, got it. We're doing the very same model. We're using the very same predictor in the metareg. We can do that because it's a dummy-coded variable already. If it had multiple categories, it would be more complicated to fit, and I'm not going to show you an example of that right now, but maybe we can follow up with that in class and I can show you how you would do it. So we've got the model being run in this case incorporates random effects assumptions just like before. So that's the mixed effects version, but we've got it, okay? And then note my warning in red, the standardized beta weight coefficients are incorrect, and we've not been able to figure out what the problem is in the calculations underlying the macro. So the other calculations are correct, so I'll stand by the metareg for that. Oh, and I should note, I've got metareg W here because on my computer, the metareg from David Wilson has to go side by side with the one from Harbord, and I'll explain more about that as we go along here. All right, so anyway, if you use Wilson's macro that you download from his website, watch out for your beta weights over here in the right column because they never quite squared. In this case, we've got a multiple R of 0.34. The beta weight should be the same here for this, but it's not. All right, enough about that. Okay, the model statistic QB will be the same as the test of significance for the covariate when there's only one covariant, which we have in the current case, and it's highly significant, so it rounds to 0. The model test is more interesting, of course, when there are more covariates, but that's going to give you an omnibus test for all of the carriers, all of the covariates in the model. And the Q residual term, you interpret it just like we were doing before. If you've got a significant Q residual, it implies there's significant heterogeneity remaining unexplained by the covariate, in this case, the country of the study. Okay. The constant in this one shows that the mean gender difference effect for studies shows the mean difference, the constant in this case shows the mean gender difference effect for studies that were not conducted in the US. So these were coded as zeros in this particular analysis in the dummy code for CO, the variable that you see there. The other one, the coefficient, gender differences are on average 0.1639 standardized mean difference units larger than the rest of the world. So you can do the math there. The mean standardized mean difference for gender in the US is, just follow it through. I'm taking these values and putting it in, and I come up with the same value that we got in the other model. So that is, the equation of the line is like this, and you fill in the values. If you put in a 1, that becomes the US. If it's a 0, it's going to reduce to the constant. So the coefficient for this term is significant, the confidence interval implying that the difference between regions is significant. Okay. The confidence intervals for the constant evaluate whether the gender difference reaches significance in non-US studies. So it's literally saying, is the male versus female difference that you have in other countries significant? And it is. Okay. So those are coded as 0 in the carrier, and that's why you get them as the reference category when you do a dummy variable model like this one. The confidence intervals for the covariate evaluate whether the gender difference is greater in the US studies than in non-US studies, and it is. So it's actually not gauging the effect size for that. That's a different test. You'd have to reverse the dummy code and redo the model if you wanted that. So it doesn't, that coefficient itself does not evaluate whether the average gender difference in US studies is significant, although you can imagine that it's clearly going to be the case. And I won't even do it because it's so clear. So, and then like in the categorical model case, the random effects variance component is there at the bottom, tau squared, and it's standard error if you want it. Here's an example using a continuous moderator, and things are a little different for it, and I think you'll see why in a second. So here we'll examine whether age of sample is related to gender differences in social dominance orientation. We run the model, it's the same as we did last time, but we put a new carrier in. And you'd follow the previous guidelines about interpretation of Q model and Q residual, and basically everything on here except for a couple of little details. The confidence interval for the covariate mean age does not include 0. That implies a significant association between it and the magnitude of effect sizes. Boom, it's significant. Okay, over here, you see the slope of that. You need to know the pattern. You've got a significant effect. Look at the pattern. Indeed, for every year older a sample gets, gender differences drop by 0.0641 standard deviations. Okay. Now, it gets a little trickier. You think about the constant. The intercept is the value of the gender difference at the point where the covariate is 0. Think about it. What are you evaluating in this model when you look at mean age? The equation of the line, let's spell it out, is just taking the terms that you see there where the arrows converge. You're taking this value, the constant is the first in my equation, and I'm going to subtract, in this case, the value minus 0.00641, which is mean, and you multiply that times the age you're trying to estimate. So if you insert a 0 here in the mean age category, of course it reduces to 0.5685. And you should be laughing by now, because essentially you're predicting a gender difference that is fairly large to be occurring at the moment of birth, before these kids can read, write, or even talk. And that effect, even worse, is significant, highly significant. So we have a great deal of confidence in predicting that a sample age 0 would show a gender difference of about 0.6. I think that's funny. In fact, in this case, I mean, here's where you should start thinking about your carriers, your covariates. No sample was younger than 14 years in this database, and none were older than 55. So, and as a caveat, in the end, age itself didn't end up being a very good predictor in this model. It drops out once we control for other factors that you could read about in the article. And I'll note another caveat. This one, we didn't do any kind of mean imputation, so a lot of cases are dropping out of this model. It's another thing to watch when you do multiple tests across different variables. That's something we should talk about further, but I won't do it in this particular talk. So that brings me to how best to show off the estimates that you're getting out of meta-regression models. And so I want to introduce the moving constant technique for you. And I should point out that I've given versions of this presentation a couple times at previous conferences. You have the details there. So a long time ago, we submitted a manuscript for publication. And I got good reviews, but one of the reviewers, I forget which one, it was reviewer 2, it's always reviewer 2, said something to this effect: standardized beta weights or unstandardized weights for your moderators tell an incomplete story. Give us estimates and confidence intervals for your effect sizes at meaningful levels of the moderators. And I scratched my head a bit because I was following convention in social sciences, because there beta weights routinely appear for meta-analyses without the extras that the reviewer wanted. So for example, you'd see things like this, that proportion of females in the sample was significantly correlated with effect sizes, and you get a beta weight, standardized beta weight in this case. Or that methodological quality was uncorrelated with the effect sizes. But it's not telling you about the levels in there. This is not telling you what the effect size would be if there were all males in the sample or all females or something in the middle. Okay, in the social sciences, you routinely see an exception for categorical models, and this is actually a lot more informative. So if gender were the moderator, maybe we'd have the same beta weight value here and a p-value, and now we'd have separate estimates for interesting levels of the moderator. Females get a significant effect, it's fairly large, whereas males get a relatively small effect, and it's not significant. So why can't we do that with continuous variables as well, would be the question, and that's where this is heading. Okay, if you look at medicine and public health, you rarely see the unstandardized or standardized weights presented in meta-analyses that are published, but they do show you estimates at different levels of moderators. It's quite common. Continuous moderators are much rarer, and maybe sometimes they're artificially dichotomizing continuous moderators, which is not a good thing because you lose power and precision when you dichotomize variables that are actually supposed to have linear effects across. So one lesson about the moving constant technique is that there's no need to dichotomize. So here's where we're going. So the way you would display trends from meta-analysis regression or meta-regression is that you might show a graph with confidence bands around the meta-regression line. And that's actually rather rare across all fields. But we would argue that such displays can be a valuable tool considering that they guide inferences about when effect sizes differ from zero significantly, classic statistical significance testing, but also in relation to important interpretive benchmarks when they're available. So that's my quest. I had to produce these estimates and confidence intervals for meaningful levels of the moderators, and I essentially wanted to take this and this kind of format, which I thought it was sufficient, but it wasn't, and I agree with the reviewer, and turn it into something like this, where I've got meaningful levels of the moderators in question, and this is the actual example that sent me running looking for guidance. Interesting levels of the predictors, and this kind of table gives you a sense of what the intervention's main features and participant features were, at least the things that were related to effect size. So the problem was I didn't know how to create a table like that. So I looked for guidance. At the time, there were other sources available, but the venerable sources, they described the theory for metaregression very carefully, very good. But they only imply how you would produce estimates and confidence intervals at different levels of solo or multiple moderators, or to make confidence bands across the range of a moderator. So my recourse was to go down the hall and visit my colleague, David Kenney. And he's the one who revealed the secret of the moving constant. I think I even have sound effects here.
Wow!
Ooh, I got sound down. Okay, so you've already gotten some illustrations to make the point, but I'll make a couple of others. So this is the one I just showed you briefly. And so we have 5 simultaneous moderators in this. I actually had to use the moving constant technique to do this particular model. Every effect that you see here is controlling for levels of the other variables. So when I look at the effect of interventions on institutionalized samples, that's the first one, yes. Now I'm contrast coding this one, so that's -1 and +1, and I'm holding these constant at their means. And so this is actually the mean effect of the interventions controlling those things at their means in effect. And the next one, I would reverse the dummy code and look at institutionalized, or not institutionalized participants, same thing. And then the same way through each of these. So I had to run the model all these different times, and every time I'm reading out the constant, and it gets very complicated, which is one caveat to its use. When you've got a big model like this, it can get really complicated and confusing. It's good to do the work with someone else to make sure you get the correct estimates. Okay. In that example, you've only got confidence intervals for effect sizes, the estimates, at particular points along each moderator. There was no figure containing confidence bands, but that example is really complex, and using any kind of confidence bands around regression lines probably wasn't in the cards for us. So the estimates in the table, as I described, holding the other moderators constant at 0 or at their means, is the solution. Here's another example. We looked at the effects of aerobic exercise on reducing depression for cancer survivors. We had 44 randomized controlled trials. And if you looked at the high quality trials, and this was all done with continuous variables, we didn't break anything into artificial dichotomies. So these are all the estimates. What you get is, these are all estimates, they're not artificially breaking it into dichotomies. So you get a dose response function in the higher quality trials. And notice the confidence intervals, okay, at 90 minutes a week, that effect is not making significance. In fact, it's so weak you don't see it. But if you get up to 120 minutes a week, 2 hours, you get a small effect size and it's significant. No more 0 in that confidence interval. And it grows as you go up to more exercise. So that's higher quality trials. And then if you look at lower quality trials, you've got no dose response function at all present. And in fact, exercise has no significant impact evident at any of those levels of exercise. So the dose response functions are appearing only for the higher quality trials. So things are getting clearer. And these are all estimates that were produced with the moving constant technique. Okay, another illustration, we'll spend more time with this one. So Kirsch et al. Looked at the efficacy of antidepressants as a function of baseline severity of depression. And so this is one of the graphs that we published there. We put regression lines in for all trials, and here's one for excluding this trial over here. So those are only the very severe or higher levels of depression. So this is the Hamilton rating scale of depression that you have, the x-axis, and this is how much improvement they saw in drug versus placebo. So positive values are actually good. It implies less depression in the drug group compared to the placebo group. Okay. Note that we have no confidence bands, and also significance between the drug and placebo groups was ignored, and significance in relation to the clinical benchmark was ignored. So here's our graph. This green line is a clinical benchmark. It's saying at what point you saw the trials get a value that, according to the National Institute for Clinical Excellence in the UK, that much of an improvement, which is 3 points on that scale, was considered clinically significant, enough for it to change clinical practice. So in other words, half of these trials, this is what our article concluded, were actually showing less than the clinical benefit that NICE wanted to see for clinical significance, which is a little damning. Okay, but we've got all these issues with it. It could be a clearer figure. So here's using the secret of the moving constant. And what we've done is to put confidence bands across the whole range observed on initial severity of depression. That's that baseline depression score. Plotting the very same thing as before. And I should point out the bubble graph here, these are heavier weights when they're bigger, and they're smaller when they're smaller weights when they're smaller. It's a handy way to show where bigger studies are. But now you can see where significant difference between drug and placebo emerges. See where the confidence bands stop including 0. The red line is 0. Okay. And then when you go over here to about the 28 mark, you finally get an effect on average of the drugs compared to placebo that significantly exceeds the clinical benchmark. That would have been a handy thing to include in our original article. So in sum, the secret of the moving constant is that the constant need not remain constant. So if you're kind of hung up on moving constants because constants are supposed to be, not moving, then maybe think about a moving intercept. So it can be quite useful when you move it, and for confidence intervals as well as confidence bands. So how do you do this? Let's talk about some ways to apply the secret correctly. So there are at least 2 that do it right. So systematic application and meta-regression macros would do. So Lipsy and Wilson's can be used for this. It's a little harder. Harbord and Higgins version directly can do it. And also Metafor for R by Viechtbauer. So here's the simple way of doing it on your own would be just systematically moving the intercept across the desired range of moderators in incremental steps. And you'd use a lot more steps if graphing if you were going to smooth the lines. And you would capture the results for graphing or tabling. So this example continues with the antidepressants example, the case. And here's a beginning meta-regression model. So now here's a beginning meta-regression model. And so we've run our model. This is the mixed effects model as I described earlier. It's a significant carrier. I mean, these are matching, as I mentioned before, they would. And as the mean baseline severity of depression goes up, the effect size gets bigger. You get the favors more depression reduction compared to placebo. Now, the intercept's not very useful. It suggests that the effect at value 0, which would be patients that have no depression at all, would actually be negative. It suggests that giving antidepressants to people who have 0 depression would actually make them more depressed. Kind of bizarre, isn't it? But the statistics can't tell you if the value that's plotted in the constant makes any sense. So that's why you have to do it yourself. And this is probably one reason the constant is so often disregarded as not useful when interpreting meta-regression results, because so often it comes out in a spot that doesn't make any sense for the phenomenon in question. Like this one. There are others. The one I gave you before with age is a good example as well. Some of these should make you laugh. So here graphically is an approximation of that model showing, and this is kind of nice because it shows that where you've got more data points, the confidence bands get closer to the line, they hug closer. We're more and more sure that we have we've trapped where the line actually is. And so when you get down here to samples that have 0 depression, of course there's no one close to that in the literature, the closest one is up there. That's why you've got such a big band, but it is significantly below 0. And that's an approximation because we actually didn't follow the meta-analytic assumptions of the previous one, and I'll explain that in a little while. So here's how to understand moving the constant. So here's again the bubble graph showing the effects that we've got in this literature. And the lowest value there is 17. Let's say we take that as our minimum that we'd want to estimate. If we were to subtract 17 from every score, we would now move the constant to 17. Simple. It's that simple. So here in this example, I've subtracted 17 from every value of the mean base variable, and I'm using a junk variable, a convenience variable, whatever you want to call it. You want to save your original values so you can use them for other purposes, right? So leave them alone. And then I rerun my metareg model, and everything in it's exactly the same except for the constant has changed. The constant is not constant. Now that constant is giving you mean baseline, is reflecting the initial severity of 17. And the confidence intervals imply no difference between the drug and placebo groups. Okay. In fact, if you look over here, they're intersecting 0, and that's exactly it. On the other end of the continuum, the highest value of depression in any of these samples was 29.444. Well, we can subtract that value from every case, and we've just changed our X scale there on the bottom so that now when the metareg model runs it, the constant will be over here on the right. Simple. So I've done it. I've replaced my values in my variable here with this value, the 29.44, subtracted from every case. I rerun the model. Everything stays the same except the constant, which has now gotten to be positive, and it suggests a marked difference favoring the drug group compared to placebo. Voila. And that's very consistent with the slope. I mean, also a difference that is far above the clinical excellence guideline. So if you were doing this in the Lipsey and Wilson macro and you wanted to have confidence bands, you would run the same model, moving the constant incrementally for each and then saving the results for display purposes. I mean, you might be able to do this in 10 or 20 swoops. And when we've done this in practice, we've run as many as like 1,000 models, since once you get a computer going, you can just sit there running. In fact, if you go and look at the assumptions in regular OLS instantiations, they routinely do exactly the same thing. So Stata runs, by default, 100 iterations of prediction points. Here's an example of their screen. So they've got their default. If you want it to be even more accurate, less grainy, you could increase that. So your computer will do those 100 models in the background and not even show you, but they're literally using what is effectively the moving constant technique. There are other options that use post-estimation techniques. So they save your model in memory and then you can manipulate it. Harburg's metareg function in Stata does this very, very well, and so does Viechtbauer's metafor for R. I mentioned these before. So if you go and look at our article for technical details, you'll see syntax there. And we even offer a Bayesian version employed post-estimation, at least in the Stata instantiation. So there's the reference to the article. I think we have it at the very end of this talk too. Check it out. And then in recent developments, a student from the seminar a couple years ago actually created a moving constant wizard that automates the process of moving the constant. So there's the wizard, and you can ask Rob about that. It might save a little bit of work. And then there's a forum as well on metaanalysisning.com where we discuss issues like this. For example, I posted, does anyone ever project moderator results beyond the extremes of the observed moderator? As you'll realize from this talk, a lot of times they are projecting beyond the extremes of the observed moderator in their constant. And so, in fact, we're doing this more routinely than perhaps we imagine. But trying to make any sense of it, I say in this post, what about projections of global temperature into the future? I mean, you want to know this because, wow, if things are going to get boiling hot out there, it could change reality for us a lot. So predicting the future has become quite a valuable thing. And in effect, you're using the moving constant technique and just projecting forward in time. It's time travel. So I wonder, why don't people take advantage of this? Why not move the constant? Let's say you apply it to methodological quality. How would your effects look if they scored perfectly on all dimensions of methodological quality that you've coded. That, I think, is a very meaningful demonstration, because now what you're doing is projecting, in theory, what an effect would be. And the beauty of meta-regression is it controls for correlations between moderators. As long as you've got enough cases in your model, you can do amazing things. So I'm going to expand on that in class when I get a chance, because it's another way to think about artifact corrections. And I've alluded that I would talk about it eventually. I don't have it in this talk, but stay tuned. Why not extend the moving constant technique, MCT, to primary level data too? Why not? Yeah, it's an extension of the logic underlying OLS models after all. It's really simple. It's just that people haven't been describing this well in those sources. The terms in regular OLS models let the modeler determine what estimates of a phenomenon should occur with different combinations. But when you do so, it doesn't permit an easy inference about where differences attain significance. But if you use the strategy, you can get a confidence interval for any point in your inference space. So it could help you with statistical inferences between different estimates from the space that you're modeling. Now, there's one method that almost always abuses the secret, at least in meta-analysis. You might be tempted to use graphing applications in SAS or SPSS or Stata. I even showed you one in this talk, because they incorporate weights and they're easy to invoke. But the problem is they're not going to match the assumptions that you've got underlying it. So this goes back to the 1985 text I referenced earlier. In standard packages, you do see that the standard errors for beta weights printed are incorrect by a factor of the square root of the mean square error. And blah, 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 you can read it for yourself. And these are the unstandardized beta weights, by the way, which is where the statistical tests are taking place. And so they need to be corrected. And this is why you shouldn't just do weighted regressions putting in the sample size, or even doing weighted regressions putting in the inverse variance, because you're not going to get quite correct tests of your terms. That's why you want to use macros like Wilson produced, or software that's dedicated for meta-analysis. So here's an example with the antidepressants example. So here's an example with the antidepressants, and it shows the actual confidence bands, which are the solid ones, being wider than the ones produced by the graphics software. So I just overlaid them for that case. Slightly different. And then here's a more extreme example, and I forget what this was. I think this might be a meta-analysis of mass media efforts to reduce risk of HIV, and we're looking at human development index as a predictor of the effects, and a strongly negative, implying that these things work much better in poor places than in rich places. It's a conclusion that appears to be holding up in our further analyses, but it's still unpublished. Anyway, we've got a mean-centered moderator. So in this case, the constant tells us where the mean is at the center of the HDI distribution. And that's quite narrow. It's only about 0.03, and this is the standardized mean differences in effect size, so it's a really tiny confidence interval. In fact, suspiciously small. But if you look at OLS graphing options, just this very same model, and as I described, over on the left side, interventions are getting really big effect sizes in poor countries, whereas over on the right side in rich countries, it looks like they're failing. Okay? Here's where the constant is in that model, because it's at 0, right? So now you got to ask, how large is the confidence interval? And if you project those lines over, you see it's much larger than the one that we were just estimating in the previous slide. So here, zooming in on the center of that graph, you see that it's actually 0.27 standardized mean differences. That's the difference in the upper and lower confidence interval, which is much larger than the so-called correct meta-analysis regression model, which was 0.03. So that's off by a factor of 9. That's pretty extreme, and it could affect your inferences at different points of that graph. So it turns out that the bias that's involved in OLS-based graphical packages, it could go either way. It will underestimate the width of the bands and intervals to the extent that the mean square error is less than 1, and it will overestimate them when it's the opposite, when the mean square error is greater than 1. So the only time the two approaches will yield exactly the same confidence bands or intervals is when the mean square error is exactly 1, or very, very close to 1. So how often do people conduct weighted regressions and naively assume that they have the appropriate estimates? I worry about it. Or when they graph them, for that matter. should use the correct estimates, the correct ways of going at it. So, and as a note, those issues are probably most severe when analysts employ fixed effects assumptions because you end up with larger mean square errors in those cases. And the example I just gave you is a good one for that. So, conclusion. We would argue that the moving constant technique, not TCM, but MCT, is highly useful to sum up much information in a compact space, both for statistical significance testing and in relation to practical benchmarks when you have them. A lot of the examples other than the antidepressants, we didn't have them, or at least they weren't clearly evident what to do. But if you have an example, you could use it. And it should help you to avoid also artificially dichotomizing continuous variables. You can produce your estimates without breaking your data, your variables in half. Caveats, well, I mentioned complicated instantiations of the moving constant technique require great care. So you see examples there. Multiple moderators get complex. Mixtures of continuous and categorical variables, odd distributions, or nonlinearities. You can do anything you want. It's just limited by your creativity. You just have to be careful when you do it. You can check out your work to make sure that you're getting output that actually makes sense. That's always nice. And then beware of increased type 1 errors that might creep in from applying multiple tests. So what we have in this one is something called simultaneous confidence bands. And you're like in that, I mentioned how you can do like 100-point tests all at once. Does that increase type 1 error? Unfortunately, at this point, it doesn't seem like anyone has studied that problem, so we don't really know. But it's a caveat I've got to give you. And with that, I'll say thank you and see you in class next time.